Welcome to our discussion on the introduction to process simulation. KLM Technology Group, based in the U.S. since 1995. KLM is a technical consultancy group providing specialized services and equipment to improve process plant operational efficiency, profitability, and safety. Today we're discussing Introduction to Process Simulation. We also offer training classes in Advanced Process Simulation with case studies, Advanced Refinery Process Simulation with case studies and troubleshooting, Advanced Ethylene Simulation with case studies, Advanced Specialty Chemical Simulation with case studies and troubleshooting, as well as other process units and equipment groups. The course descriptions may be found on the website www.klmtechgroup.com/training. The Kolmetz Handbook of Process Equipment Design. There are multiple chapters for distillation design in the handbook. We have over 50 individual chapters on a wide range of subjects. Each chapter is 80 to 100 pages, including design and sizing guidelines. As we revise the chapters, we're adding troubleshooting in each section. The handbook may be found here. KLM Tech Group, Engineering Design Guidelines. Some of the distillation chapters include general distillation design, trade column hydraulics, which we'll discuss today, packing column hydraulics, refinery crude tower, refinery vacuum tower, reboilers, BTX extraction units, ethylene plant quench oil towers, quench water towers, ethylene plant C2 splitters, ethylene plant C3 splitters. Our discussion today, we're going to have some introduction, case study, ethylene depentinizer, some guidelines, and some conclusions. Simulation is a powerful engineering tool that is widespread use in the chemical processing industry. Utilized correctly, can help design, optimize, and troubleshoot process units when you follow guidelines developed from the fundamental basics of engineering. It's important to remember that machine calculations are for the purpose of improving only the speed of the calculation. It is up to the user to input the correct data in so you can get the correct data out. Despite rapid progress in computational speed and user-friendly interfaces, understanding the rules and the limitations of simulation tools is still a prerequisite to obtain the simulated results close to those measured in the field. We want to have a design, we want to troubleshoot, and we want our simulation to be very close to those measured in the field. The user needs to supply the correct input data, interpret errors that occurred, and make critical judgment on the results. Mastering these techniques often requires substantial field experience and practice. Accumulating such knowledge in the form of design guidelines can help users to ramp up their learning curves. Working steps like the correct selection of actual field efficiencies. In general, a process simulation will have 100% efficiency. But we know in the field, they're going to range from less than 50 to maybe 85. So, what is the correct efficiency? We know we choose the appropriate vapor and liquid equilibrium data. So we know different types of hydrocarbons and chemicals react differently when mixed with each other. And we put together correlations for these mixtures. So simple alkanes, maybe polar components, maybe high hydrogen, maybe hydrocarbon and water mixtures. All of these require a different vapor and liquid VLE package. Feed modeling. If you have a very high feed velocity, if you have a very large column, it's probably a good idea to model the feed. An analysis of the actual hydraulic behavior all have a strong influence on the accuracy of the model's results. It's important to understand hydraulic behavior. I've seen hydraulics not being designed properly have as much as a 20% reduction in efficiencies. Developing guidelines for each of these is very important. What efficiency should you use? What VLE package should you use? How should you model the feed? How do you design the tray with hydraulics? Developing guidelines for each of these steps is very important to a practicing simulation user. Without the actual field efficiency, if your simulation is very different from what's actually in the field, energy usage may be very high, product recovery will be low, product purity will be low. You might not even make your specification. And each one of these things costs money. Let's look at a case study. An ethylene plant where I worked in Malaysia wished to convert a gasoline hydrotreater stabilizer column to a depentinizer column. The stabilizer was designed to remove C4s and lighter hydrocarbons. Stabilizers sometimes are called debutanizers. Now they wish to remove the C5s and lighter hydrocarbons while minimizing the benzene C6 loss in the overhead. Original column had 28 sieve deck trays with a bottom diameter of 1.8 meters, about 5 feet, and a top diameter of 1 meter, which is about 3 feet. Original design feed rate was 16 tons per hour with a bottom specification of 1% C4s and lighter. So it was hydrogenated pie gas. We came in, overhead condenser, overhead receiver, reflux pump, reboiler, bottoms to storage. A good place to start in a revamp would be go research what has been successful and not successful in the proposed revamp unit operation. Unfortunately, there are over 900 published cases of unsuccessful distillation operations. Henry wrote a paper on this. If there are 900 published cases, there's probably a 10-to-1 ratio between published and unpublished. So there's probably 9,000 actual cases out there. There were 400 published cases of refinery tire incidents. They include vacuum columns, atmospheric columns, debutanizer columns, which is what we're looking at today, FCC main frac, de-ethanizer, depropanizer columns, which is what we're converting to, alky main fracs, Coper, naphtha splitters. The largest number of cases was in a vacuum column. It's one of the most difficult to simulate. And to use hydraulics and have it match the field data. Damage, 27. Coking, 21. Intermediate draws. Misleading measurements. Measuring is harder than you would guess. Plugging, installation mishaps. There's been many installation mishaps. Abnormal operations, startup and shutdown. Startup is when over 50% of the damage happens on startup. It's very important for you to understand startup. Maldistribution, weeping, and condensers. The top 5 causes of damage in vacuum columns: water-induced pressure service, insufficient mechanical strength, broken nozzles or headers of spray distributors, high bottoms level, which is very, very common, packing fires, which is common. A lesson to be learned that is possibly 1/3 of the causes of damage in vacuum columns can be prevented from the design and operating procedures that adequately prevent water from entering the tower. We add steam in the bottom of this column. If there's wet steam and water is allowed to come in, we know the ratio of water to steam is about 1,000-to-1. So if I let water enter this hot column, it's going to act like a mini explosion because it's going to go from 1 cup of water to 1,000 cups of steam. And whenever I see a tray that looks like this, it's a good guess that they've allowed water to go into the column. Looks like a mini explosion there. A joint design operations, hazard, and operability review should focus on the listed potential problem areas. It's a good idea to have a ballpark range of what the correct answer should be before you begin to simulate to prevent the 901st case. Many successful depentonizers have about 38 to 45 trays. Average tray efficiencies have been about 75 to 85%. For our design case, we utilized 70%, so we were very conservative. We didn't use the bottom range, 75. We for sure wouldn't use the upper range of 85%. And there are many shortcut methods to establish the number of trays and reflux ratios based on the relative volatilities of the light and heavy keys. A second step might be to simulate the original heat and material balance provided by the licensor, and then simulate the current unit operations. The current unit operations may need a test run with data analysis to develop an accurate current heat and material balance. Most flow meter accuracy is only about 2%. If these two cases can be matched, so if the original design can be matched and you can match what's in the field today, you can then use that model to project the future cases. Without accurate models that match the original heat and material balance and the current operation, future projections are a risky adventure. Step 3 would then utilize the tune model to verify if the existing tower can be utilized, possibly by raising the reflux, adjusting the pressure, or other simple modifications. Step 3 is really two parts. Part 1, modify the tune model, then rate the tray hydraulics. There are 2 chapters in the Kolmetz handbook that talks about rating tray hydraulics and then rating packing hydraulics. In this case, the client desired increased capacity and increased separation ability, which is difficult to achieve in an existing column. The existing column could not easily provide the increased capacity and separation. A design was developed utilizing the tune model, which met the desired capacity and separation. Proposed new tower had 40 stages. This required a 1.8 meter bottom and a 1.2 meter top diameter. So the old had 16 tons, distillate. We didn't want any benzene, but in a debutinizer it's rare. Bottom's product about 1%, C4 is left in the bottom. The new was 19 tons. The benzene we wanted 0.01 max, and we wanted C5 plus in the bottoms to be about 1%. Design of the new 40 tray hydraulics. So max recommended jet flood is about 83%. At 83% jet flood, there's about a 95% confidence level. The jet flood is a vapor limitation. So we build our correlations for jet flood by running thousands of case studies in columns. FRI has a column where they've run thousands of cases, and we make a correlation. There's some cases above the correlation line, there's some cases below the correlation line. So for your particular column, you may be one of the ones that's above. So we really don't recommend you go above 83% jet flood. For a new system, I design about 70%. For a new system, you should not design below 50%. Below 50% jet flood decreases your tray efficiency. I've been surprised how many times somebody will come up and show me a 30 or 40% jet flood on a new set of trays. They're not grasping that this jet flood has a huge effect on your efficiency. Downcomer backup. The most downcomer backup, this is a liquid limitation. It's about 80%. For a new system, I'm going to design about 60% downcomer backup. Guidelines for the field. Investigate previous operations. Simulate the original heat and material balance and tune the model. Simulate the current operation and tune the model. Rate the existing tower. Look at the hydraulics. Recommend proposed changes if required. Investigate previous operations. There's a huge database of knowledge. VLE data, what should you use? Tray efficiencies, normal designs, what are challenges in here? One thing you need to do is make industry friends. You need to have a group of friends that you can call up and ask questions. And then you have to be a friend. If they call you up and ask you something, you need to be willing to help them also. Simulate the original heating material balances. Most licensures have good heating material balance developed from plant operations data. VOE data. Tray efficiencies can be verified. You should be able to quickly match the original heating material balance in your simulation. Simulate the current operation and tune the model. This can be a challenge. Sometimes not all the instrumentation's there. Pressure, flow, temperature measurement can be an issue. Sometimes you have to run a test run and reconcile the data. If you cannot match the current original heating balance and the current operation, you may not wish to use this model for a revamp or tower ratings. Rate the existing tower. Can the tower with operational changes meet the desired products? In one case, we were able to match the heat and material balance. We were able to match the current operations, but we were not able to match the product purities. Went and did some other research. It was pretty close to the things I found in the field. So we sent the samples to an independent lab, and then the independent lab was able to verify that the product purities were being met. Rate the column. Then utilize the hydraulic analysis of simulated internal vapor and liquid flows. If you're really going to be a good simulation person, you also need to have hydraulic knowledge and a small amount of knowledge of how the trays are designed. It will help you in your simulation. Recommend proposes change if required from the tune model. Now design the new equipment specifications. Sometimes you may want to do things in a stepwise fashion with the highest return on investment items implemented first. What are some tray efficiencies? Well, the simulation uses 100%. I will typically remove trays based on what I think the tray efficiency is. So if it's a 30 tray column and it's 70%, I might only simulate 21 or 22 trays, something like this. So 70 times 3 is 21. Demethanizer, deethanizer. Deethanizer 70, depropanizers are 75. One thing that's interesting about this table is C2 and C3 splitters. The boiling points for a C2 and C3 splitter are very close together. So for things that boil close boiling ranges, when I go to the field, the efficiency is high, like 85%. If I have something like hydrocarbon and water, where the boiling points are very far apart, the efficiency is very low, about 15%. So for a depropanizer that I'm using 70%, for the trays I'll use 70%, for the reboiler you use 100%, and then for the overhead condenser you use 100%. Low relative volatility gives higher efficiencies, and that's what I talked about. If the boiling points are close together, you will have higher efficiency. Vapor and liquid ratios affect the efficiency. Process simulations assume equal vapor and liquid ratios. All right. Very high or very low hydraulic rates decrease the efficiencies. All right. So if I have a jet flood very high or if a jet flood very low, that is going to decrease the efficiency. Packing, the same effect. If the relative volatilities are the boiling points are close together, you get higher efficiencies. Liquid vapor ratios affect efficiencies. Very high hydraulic rates decrease efficiencies in packing. So there's a recommended of 50 meters cubed per meter squared. In packing, liquid to vapor densities are also very important, particularly above 10 bar, 150 pounds. So if your vapor to liquid densities are close together, you should not use packing above 10 bar. There's been many failures above 10 bar in packing because of this vapor to liquid density. Choosing tray hydraulics. Recommended 83% jet flood. Recommended is about 80% downcomer backup. Jet floods on the vapor side. Downcomer backups on the liquid side. Choosing packing hydraulics. Capacity decreases as packing surface area increases. Avoid bed heights that are higher than 6 meters, 20 feet. A rule of thumb is about 15 stages max per bed. Most common reason for loss of efficiency with operating pack columns is poor distribution. Higher surface area packing requires more distribution points. And we talk about this in the chapter on packing hydraulics. Challenges. Here's a large challenge. One engineer runs a simulation, like for a licensor. A second engineer runs the hydraulics, and a third engineer designs the trays. Each of the other engineers assumes the other engineer has adequate safety margin in his design. They can be employed by 2 different companies in 3 different locations. It's important that there's adequate communication among the designer. So I was reviewing one column, and the simulation had no safety, the hydraulics had no safety, and the design had no safety. So when we got ready to pass the performance test run, we did not pass the performance test run. Process simulation is a powerful chemical engineering tool that has widespread use in the chemical processing industry. Working steps like actual field efficiencies, VLE packages, feed modeling, analysis of hydraulic behavior, all have a strong influence on the accuracy of the model's results. Developing guidelines for each of these steps is important to a practicing engineer. Rating process simulation programs. In the October 2017 Engineering Practice magazine, we published an article that rated different process simulation programs. There was a great team of 6 people that volunteered to rate each of the program. The magazine can be found at www.iacpe.com/magazine. There's multiple issues of the magazine there. They're free. If you want to look at this particular program, go look at the October 2017 Engineering Practice magazine. KLM's core businesses, of course, we do training. We have the Kolmetz Handbook of Process Equipment Design. We do process optimization studies by simulation, by doing test runs. We do HAZOP facilitations, and we provide engineering support. If you've searched really anything on process equipment, you've found the Kolmetz Handbook of Process Equipment Design. This was the first chapter we wrote. Piping, hydraulics, fluid flow, line sizing, and material selection. Rev 1 was in January of 2007. KLM has a very senior group of associates and trainers that can assist your team. We can teach in regional seminars at your facility and in webinars. We have a large group of courses that we offer on the website, klmtechgroup.com/training. Thanks for your time today. Introduction to process simulation. All the best for your career and family.